Thank you for the very kind introduction. My topic will be on fast and precise MR. So, as we know, MI is slow and we're trying to speed it up. It's slow because you're trying to take multi-contrast image and each scan can take a few minutes. So the scan session can be 20 to 30 minutes. And the main bottleneck is that you're acquiring data one line at a time, about 80% or 90% of the time, and you do a little bit of EPI. And that's pretty much it. But if you move towards more efficient data acquisition strategy, with rapid single shot as well as non-Cartesian trajectory, you can cover k-space much faster. You can also do time resolve imaging, acquiring KT data to get joint multi-contrast acquisition together with EPTI and MRF acquisition. So employing these more advanced techniques, you can do things a lot quicker. Here's an example of a rapid 3D MRF acquisition at 3T, where you can do this in literally a minute or two at 1 millimeter isotropic whole brain for T1 and T2 and get nice synthesized contrast that would have taken about half an hour to acquire in a clinical scan. You can do other contrasts such as the T2 star and QSM distortion and blurring free with multi-shot EPTI, sub-millimeter resolution at 3T in just over a minute, or even more complex joint diffusion relaxometry acquisition to get into multi-tissue compartment with a diffusion prep MRF in just a few minutes as well. So leveraging all these efficient acquisition strategy and applying it to the next-gen scanner, we're now able to get half millimeter voxel size across the whole brain in just 3.5 minutes with MRF for T1 and T2 mapping. Then you can synthesize all these contrasts, be it MP-RAGE, MRA, or T2, flare, and double inversion recovery. I'm getting around 400 slices across the volume. So the encoding time is about 0.5 second per imaging slice at close to 400 matrix size across all these contrasts and quantitative information. So with such technology, you can synthesize things like an MP-RAGE, which give great gray-white matter contrast, but not so much deep brain nuclei contrast. But if you look at the T2 in the deep brain area and kind of scale up the contrast of it, there is contrast in the deep brain area. So you can synthesize the T2 prep MP-RAGE. Now you have both gray-white contrast as well as deep brain area in just one sequence. So this is all great. Why don't we do this all the time? And it's all in the detail. It's you need quite a bit of detail characterization of system imperfection. At 70, you have a lot of B1 and B0 in homogeneity, so you need to correct for those. We've developed a way to calibrate this out quickly and incorporate that already. But there's also few imperfection, particularly in the powerful head-only system, requiring you to use scope, field camera to really calibrate it and incorporate that information in the reconstruction. This can be time consuming and kind of expensive equipment and having a new postdoc to train to try to use this. So it's going to take a bit of time to do. So let's see if we can do something different without these type of equipment. So first thing, we can start easy looking at fixing nonlinear ghosts in EPI. As people have talked about, Renzo has identified this problem where the gradient imperfection is not linear, but also nonlinear, but also changing along Kx and Ky. And this gradient imperfection coupled pretty badly with parallel imaging and cause severe artifact as shown here. First, you can try to fix some of this problem using dual polarity grapher that John Polomini and his group came up with nicely, where you use two different grapher kernel, one for the even and one for the odd lines, to help clean up the nonlinear ghosts between even and odd. And that cleans things up a bit, but it's not quite there yet because the field imperfection is also changing along the Kx direction. So Renzo came up with a nice, neat approach where he acquires acquisition and dual polarity and average them. And the image looks gorgeous, but the problem is your temporal resolution is half. So we thought there needs to be a better way to get to this type of imaging as well. And inspired by John's work on dual polarity grapher, can we actually not only have grapher kernel in the even and odd line, but also different grapher kernel along the Kx direction? and then use the same fitting where we're going from the single polarity data to the dual polarity average clean data so that those grappa kernel can clean out the few imperfection as well. So this should work, but now you have a family of grappa kernel. Instead of two, you will have two 300s. And there's not enough training data pair for each kernel because there are only 1kx position per kernel. So this is going to be tough. The nice thing about these grappa kernel is that they don't look that different from each other because the few imperfections just change gradually along kx. So we realize we can represent a family of grappa kernel very compactly using a small MLP. And we can use this, we can train using the whole data set to train one of this MLP network so we can officially use all the training data to calculate all the grappa kernel. So that's the gist of it. And we try to do this on a 3T system at Stanford. And here's the reference image. Grappa has some artifact, dual polarity cleans it up. And our field correcting grappa, which also account for eddy current along KX, cleans this up a bit further. Apply this also onto the impulse. And you can see here that this is 0.8 millimeter isotropic for acceleration. Echo spacing is short at 0.6 milliseconds. Single shot has quite a bit of artifact. Dual polarity cleans it up a bit, and then field correcting grappa really polish it up to get nice result. So now that we came up with this MLP-based grappa idea for EPI, can we extend this to do field correction or field estimation for arbitrary type of k-space trajectory? And the answer is yes, as long as you have a pair of clean and dirty data to train the MLP grappa kernel on to interpolate between them. So here's an example where you have a spiral data that is this KT traversal with some eddy currents and field imperfection. And if you have a clean KT data, you can apply this quickly via doing EPSI or EPTI at a low slew rate, so you don't have a lot of imperfection. And then you can train a bunch of grappa kernel to go from one space to the other. Each grappa kernel doesn't have a lot of training data, but they also are very related. So you can use an MLP to do that, to jointly train them efficiently. And once you do that, the grappa kernel in the MLP represents the field imperfection, just like how spirit kernels represent Coy sensitivity. So we came up with an algorithm analogous to how eSpirit can get Coy sensitivity from spirit kernel. We can get basically field imperfection every single time across the whole spiral readout from the MLP grappa kernels. So this is our festive result for spiral compared to scope, and they look pretty similar. So what's going on here? We're doing field estimation without field probe. Field probe has 16 channel probes. We have 32 or 64 channel coil plus a 3x3 or 5x5 grappa kernel. We have plenty more variable to be able to estimate potentially even better than scope. So let's look at this for the magnet scanner. This is a 3T 0.85 millimeter single shot variable density. 30 millisecond readout can be done quickly. Our festive calibration of clean and dirty data takes about 35 seconds right now. With some tweak, we think we can get it down to about 15 seconds. And from here, you can see the estimated field pretty much match that of scope. There's some small variation, but I'll show you the recon of this and you'll appreciate it. So this is the phantom result. Scope looks pretty clean. Without any current correction, it has quite a bit of artifact, and festive looks pretty clean too. But if you zoom in here, there's still a little bit of difference between scope and festive. But if you focus on here and look at the residue, it's actually cleaner on this sequence. Right? So we have the potential to actually get better field calibration than scope. There's still further characterization to be done, but this can be done in 30 seconds or less now. We can extend this idea to map out spatial temporal changes in eddy current. Normally, people just use eddy current as a fixed eddy current field along the readout, but it's not. It actually changes throughout the readout because it decays away. So you want to map spatially and temporally, we can use the same technique with festive, map this out for GX, UI, and GC gradient, and use a linear model to then interpolate for spatial temporal eddy current across all the diffusion directions. This takes about 5 seconds to do. Here's our spiral data without the eddy current correction, and here's with from this 5-second calibration scan. So throwing all this stuff together, what we can do, let's look at spiral diffusion at 3T. Um, Here's an example of baseline corrections just at B0 and spatial temporal eddy current correction. It looks quite blurry. Add in the calibration from Festive to get the trajectory right. You can see it's a lot sharper. And we can still do a bit further. We have autofocus to account for breathing and B0 changes due to heating and eddy, long-term eddy current as well. And it sharpens up a little bit further still. So what do we have here? Combining Festive with this tailored autofocus approach that we've developed, we can now do concurrent field monitoring without field probe. So this is preliminary data. With spiral, you get very short TE. I think TE is around less than 20 milliseconds in this case. We did 0.85 millimeter in plane 2 millimeter slice, 3-minute scan, V1000. You can get pretty nice result here. We haven't put in the multi-band yet. This was one of the data that we got, and GE, when we visited them in New York, was still waiting for our system to arrive at Stanford. Once we got our system, we can do a bit more stuff. And the hope is to get 0.85 ISO whole brain in a similar time frame of just a few minutes. Okay, so I've talked to you a bit about how to do fast and precise imaging, and the question is, can you still achieve this in the presence of motion? So there's been a lot of nice work looking at motion estimation, again, using multi-channel receiver array. You have a lot of information here. People try to do this in the recon by jointly estimating motion and image by looking at maximizing data consistency, and this works quite well. However, it's hard to do really well when you do high parallel imaging acceleration, so motion can't be estimated too well there. So we'll develop an approach to supplement this, where we recognize that at every beginning of every sequence, you have a short dummy scan. So let's replace that dummy scan with a short scout scan, where we're going to acquire calibration data, basically row rest image as a scout. And utilizing that scout, along with the K-space data that you acquired during the acquisition, you can estimate motion much better. And in this case, even with acceleration of 6, you can still recover quite a bit of information with the same image. Let's go into the detail of the weeds a little bit. So the same motion estimation works best when you're comparing low K-space data that you acquire during your scout with the low K-space multi-channel data that you're acquiring during your acquisition sequence. And you're just looking at how things change to estimate the motion. However, the low-res K-space data during the data acquisition might not be acquired regularly. So you can't estimate motion that well throughout the sequence. So you have to do a little bit of tweaking to the sequence. Here's an example of an MPRH sequence where you can see here per KC encoding, you acquire volume TR. Here is the scout region that we acquire low K-space data on. So with these early TRs, you're not having overlapping K-space data with the scout. So you can't really estimate motion. So what we can do is we can reorder things a little bit, acquire these lines, but jump in here for a few lines per TR volume so that we have matching data to the scout to estimate motion. Also, we can go another way where we're just like, well, screw it. We're just going to throw 4 lines away and always acquire the center of K-space region with those 4 lines, and so that we can use to compare to the scout per TR volume. And that works pretty well as well. So what happens if we want to go to a higher temporal resolution of motion estimation? We may be able to add these guided lines throughout the whole volume acquisition. The problem is that the contrast changes because the signal evolves over time. So your guided lines to compare to the scout data is not going to be that good because the contrast mismatch. So you can't estimate the motion that well. So we have a way to fix this now. The way to fix this is to recognize that we can actually acquire quantitative scout quickly. Here's an example of an MRF 4mm scout that takes about 7 seconds. Once you have this, you have T1, T2, and PD maps. You can then create any contrast synthesis to create scout at different contrast level. And then you can add in these, instead of guided line, you can also use in short navigators. And then you can compare the navigator with a matching contrast scout to estimate motion whenever you like across the sequence. So we've been able to do this and get really nice result for MP range across the different inversion time. Also extend this to an MRF sequence. This is our standard spiral projection MRF acquisition. You have an inversion prep with 500 TR readout and some wait time. During that wait time, we typically put in a short navigator, a volume navigator, to get motion estimate every 7 seconds. But if you want to go faster, what you can do is then add in these compact navigator throughout the sequence every half a second or so. Add a Q scout up front to replace the dummy time so it doesn't add to the scan time. This is the first dummy period. So you get multi-contrast scout data and compare the two to the matching one and get temporal resolution of about 0.6 second motion estimate. So let's look at how that works. Here's an example case where there's a dedicated person went in and banged his head against the scanner. No correction, looks pretty bad, but even with the VNAV correction at every 7 seconds or so, temporal resolution is not enough to capture these variation. So what ended up happening is that it actually makes things a little bit worse. But now with the Queen approach, we are capturing motion every 0.6 second, and we're able to recover quite a bit more information here. Okay, so capturing motion sub-second is great, but it's also important to track B0 changes, particularly for T2 star and QSM sequences at late TE. You can capture the 6 rigid motion, but due to the motion, there's going to be changes in B0 as well as from breathing and other things. And these can be quite smooth at 3T, but at 7T, where we're operating here, can go up to 5th or even 8th order spherical harmonic. And you really need to capture that to be able to get clean image in T2 star and QSM. So we'll extend our Queen approach and develop the SMINA approach to tackle this issue as well. So Nan's been working on this. This is a standard Jerry acquisition. We can acquire a quantitative scout using a quick EPTI scan at 4mm up front. Then we insert in these navigator, basically the compact 3.5 millisecond navigator, so that it doesn't change the whole module. It's KT encoding across for echo. We acquire complementary one across 4 TRs, combine them and compare it to our time resolved scout scan. Estimate motion, we have some nice model to do this. So we can estimate motion in up to 8th order spherical harmonic, B0, every 200 milliseconds. So here's some result for large motion at 3T. You can see here up to plus minus 5 degree in millimeter, no correction, some blurriness, some correction with motion only cleans it up a bit, but motion with DB0 really clean things up nicely. Here's another example where we actually didn't move, but we actually tell the subject to breathe deeply, and there's quite a lot of changes in B0. So here's an example with EPTI acquisition with deep breathing, you get some fuzziness in the image. And then if you correct for both motion and DB0, things clean up nicely. Last example here is on the 70. This at Stanford where the motion is quite large. And with this large motion, the field change can be up to 8th order spherical harmonic. This is still our preliminary data, but it looks promising. No correction is pretty bad. Motion correction didn't really help because there's a lot of field changes at late TE. 2nd order helps a little bit, but you really need up to 8th order to clean things up. Okay, last slide. I kind of skimmed over this before, but how do you actually reconstruct this stuff? How do you incorporate large-scale motion information into the reconstruction? Typically, people can do align sense reconstruction where they build in a separate forward model for each motion state, accounting for background phase changes, as well as coil shading changes as the head move. And then the recon time and the forward model size will scale linearly with the number of motion and phase changes. So this is quite rough because now if we're tracking motion every 200 milliseconds, we're going to have thousands of motion in DB0 state per acquisition, and the reconstruction will really blow up, and you can't really recon this, particularly if you're doing subspace recon for EPTI or MRF acquisition, right? So Yimeng came up with a nice way to fix this. So instead of expanding the model, we can touch the data term instead and try to clean up that motion corrupted data. And we're going to clean it up using grapper operators because we learned that grapper can interpolate case space as well as fixed field imperfection. So we can use the same idea of graph a kernel per k-space position and per motion and dB0 state to clean that data from gridding, field coil weighting changes, and background phase changes. We just need a family of them, and we know how to do that. So we have a family of cleaning graph kernel that we can train in a few seconds and then apply quickly, probably about 10 seconds to do per acquisition. It's a 3x1 kernel. It has negligible G-factor noise because you're just using it to do smooth field change correction. And then the recon time will then become essentially the same as in the motion case. So this has been a really nice complementary approach to our navigator to be able to reconstruct this large motion data and information. Okay, so I'll talk to you about fast imaging with strong gradient and fast K and KT encoding, seamless estimation of field imperfection with festive, and sub-second motion and dB0 tracking with quantitative scout and navigation. Thank you. Now